This is Read the Source, episode number 22. We are here today with Cornell,
Hi guys.
myself, Eric, and our guest today, who has been a guest here before, is Richard Feldman.
How's it going?
Awesome. So you came on for a previous episode on Elm CSS, which you did, and since then you've done a book on Elm in general.
Yeah, it's true. Elm in action. Could bring that up. I guess we could put that in like the notes or something.
Yeah, and we also, I think I heard you. I don't know if other listeners follow JavaScript Air, but I heard you on there for an episode as well.
Oh yeah.
Talking about transpilers and the different types of two JavaScript languages as well.
Yeah, that was fun. Also, there's a from Ben Masters doing this too. 2-day workshop on Elm. That should also be a good time. That's coming up soon.
Front-end Masters is awesome stuff. So
Yeah.
it'd be awesome. All right. Sorry, go ahead. You're gonna go through some stuff today.
Yeah, definitely. Going to talk through elm-test. Did you have any other stuff we should mention before we dive in?
Well, yeah, we're going to go through the node test runner that you did, elm-test, and kind of how the testing works, some examples. So there is some core knowledge of Elm that's just sort of understood. So if you're not familiar with Elm, definitely read Richard's book, check out some tutorials, and try and follow and come back to it. After you get through stuff. And I'm going to ask some naive questions too, because I'm not so familiar with Elm, so hopefully that'll help if you're not so familiar. But I'm going to try and not jump in too much because we want to kind of go through the code more than not, since this is Read the Source.
Absolutely. Cool. So this is elm-test, and importantly, this is elm-test 2.0. So Max Goldstein and I went through and did a revamp of this from the old elm-test, and we had a couple of goals. One of which was that we wanted to integrate fuzz tests, or this goes by many names: generative tests, property-based tests. But the general idea is taking a test and running it a bunch of different times, like 100 times, with different randomly generated inputs. So the idea is to get sort of higher test coverage and covering more cases and try to expose corner cases without actually writing more code, just by throwing random numbers at it. So this is what the API looks like that we came up with. So this would be one individual test. So you write test, and then this is not a fuzz test, this is just a unit test. So you say test, this is just a plain old Elm function. You give it the string for the description of the test. So we're saying string.reverse has no effect on a palindrome. You can nest these describe things to organize your code a little bit better. You can nest as many of those as you like. Then we're passing the test. This is just shorthand for parentheses, basically. This is an anonymous function that takes unit, which is to say it takes effectively no argument. So this is sort of the JavaScript that would just be like function blah. It's just like an anonymous function wrapper around it. And the reason that we did that is so that these would not all get evaluated. So that was a problem with the elm-test 1.0, is it didn't have this. And so right when you would load your tests up, because these are all synchronous, it would just immediately evaluate all of your tests, before the test runner could do anything. So you couldn't get progress bars if you had a lot of tests, or any kind of incremental feedback as the tests were running. It was just if you had 1,000 tests, right when you loaded up the file, they would all run and it would just freeze until it was done. So now we wrap them in functions, and we can make things a little bit nicer in the UX. That also means we can parallelize these later, although I haven't done that yet. Okay, so then inside this anonymous function is the body of the test. So I've just put a let in here, palindrome equals Hannah, and then I call expect.equal palindrome string.reverse palindrome. So I'm just basically claiming that since Hannah is a palindrome, that is, it reads the same way both left and right. that if I reverse it, it will still equal the original. So expect.equal is designed to be used in this pipeline style instead of in sort of a normal function calling style. So again, here's another test, anonymous function. So basically, I start with by building up the value that I want to test, and then at the end, I expect.equal the sort of the expected. So this is sort of I'm building up the actual, and then at the end, I say expect.equal, and then some sort of thing. And so then this is the fuzz test, which essentially looks the same way as the unit test, except that you add an additional argument here. So you say fuzz, and then you say the type of randomly generated thing you want to generate. So you can say string. You could also say like list string, like if you want a list of strings. And then basically whatever you put in here is going to get put into this function. So for unit tests, it just takes unit, which is useless. But for fuzz tests, it actually gives you something useful, a randomly generated string. And then you can just take that randomly generated string and work on it. So the difference between this and the other things is that it's actually running this 100 times. This anonymous function will get run 100 times with a different randomly generated string each time. So I'm sort of getting a higher degree of confidence that this claim right here is true. I'm saying that if you give me a string and I reverse it twice, then I should end up back where I started. And if we're doing that with randomly generated strings, then I'm more likely for that to be true. Okay, so that's the API, the testing API. There's a bunch of different stuff, and like there's not just expect.equal. There's also like greater than, less than, not equal, true, false, stuff like that. Okay, so let's talk about how this code is divided up. So this right here is the elm-test package. So we can look up the docs. So this has like expect, fuzz, test, and test.runner. So the reason that this is divided up this way is that you can write multiple different test runners for this. So I've written 2 of the test runners, but if people want to write their own test runners that do different things, they totally can. The idea is that this API is just sort of a way to describe a series of tests, and then a test runner can just consume that API and present the results in a certain way. So one of the node test runner is sort of the go-to. If you do npm install -g elm-test, this is what you'll get. And basically, it's just your totally standard CLI-based test runner. So here's what I'm in that directory right now. So I'm in the examples directory, and there are 2 tests in here. There is failing tests and passing tests. So I'm just going to run the failing test real quick. Cool. So this is okay. So at the end, it tells me test run failed. Here's the duration. Here's how long it took to fail. Nothing passed. 18 of them failed. So that's kind of expected because this was the failing test. So here's the output you get. First, it compiles all your Elm code, and that's just running through the normal Elm compiler. It just sort of does that for you, so that you don't have to compile it separately. And then here's the sort of relevant test output. So it says running 18 tests to reproduce these results. Run elm-test --seed with this. So the idea here is that when you're doing a bunch of stuff with random number generation, it's pretty useful to be able to reproduce these things. So I might want to copy paste this over and send it to my coworker and say, hey, I had these failures. Here's how to reproduce these failures so we can work together and figure out how to solve this. So if you do this, you will get exactly the same failure output as what I just did here. So here are some failures. So I have a description of something called without nums. Adding numbers to strings has no effect. Let me actually bring up the code for that. Oh, I've got let's see. Okay, so this first test here is without nums, and if I open this up, it's going to be failing tests. Okay, so basically what I'm saying is take all of the the numbers out of this string. So I'm filtering out any character that's not a digit or a dot. And so kind of the purpose of this is that I'm claiming that if I take, actually this is kind of a bad example. I just realized this is kind of more complicated than it needs to be. So the relevant part of this is just looking at the output here. So it tells me what things it was using as randomly generated inputs. So it used an empty string for one of the strings, and then this gigantic negative number, and then empty string for another one. And then basically, this is what we got, and this is what we expected. So we got a dash, but we expected it to be empty string. So kind of what this function is claiming to do is you take two randomly generated strings, so maybe like foo and bar instead of empty string and empty string, and you stick them together. So like foo, and then bar, and we want to stick those together. But what happens if you stick a number in between? So like 5.5, and then if I call without nums on this, it's supposed to take out the number. So it's supposed to just translate that into just foo bar instead of foo. So it goes from foo 5.5 bar to this. And there's a bug in this, which is that it doesn't know how to handle negative numbers. So the idea is if I pass this in here, it will go from this to this. And I'm trying to make my test detect that. So the test thinks that it ought to be this, but it actually is going to be this. And so all of these tests fail for negative numbers. If they get any negative numbers, then it fails. So the reason that you're not seeing foo and bar on the sides here is that the fuzz test does this thing called shrinking to try and find smaller inputs that reproduce the problem. So it's shrinking this string all the way down to empty string. It's not able to shrink this float any further than this, but it is able to shrink the string and say, okay, so yes, foo and bar reproduce this. Also, a huge string reproduces this, but empty string is sort of the smallest one that can reproduce it. Okay, so let's go through some of the code for this.
Before we start that, I just want to say anyone who's listening to this, if you want to see those tests, those failing tests, they are in the repository for the node runner, which we posted on the Google Plus event.
Yeah, and I'm realizing now that I'm on the internet broadcasting this to everyone that these are like relatively these like demonstrate that it works, but they don't actually give you a good idea of what it's like using the library. So I realize I should probably change these to be more real worldish, because you look at this and you're like, there are a bunch of empty strings and like a dash, and like what does this mean? I guess the examples in the docs are probably a little bit better. So like expect equal.
That's the next project, to have like an interactive console on the docs, right?
That'd be cool. Yeah, so this would be an example of a test failure that has like something more, like longer in it. Like if I had this list of things and it's I expected it to equal this. The reason that the output is lined up like this is so that you can sort of look at these and sort of visually diff them and see, wait, why are these different? Oh, I see this first string is a little bit different than this one where it's two strings, things like that. Okay. Right. So let's dig into the code here. So this is the node test runner. I want to just start with the elm-test API itself. So we've got this module called test. We're exposing tests, fuzz options, describe, stuff like that. So describe and test were the first two that we looked at. We've got our documentation comment up here, which is what generates those docs on the package website. So let's just kind of go through some things. So the first thing to note here is that we have this type alias test equals internal.test. So the purpose of this is hiding the implementation. So we're using test.internal here, and this exposes basically everything that you need to put all of these tests together. So we have this union type called test. a test wraps a function that takes a random seed and a number of tests to run, and then returns a list of expectations. So an expectation is one of these expect things. So expect.equal, for example, returns an expectation. Not equal returns an expectation. Less than returns an expectation. All those things. So what this means is that when I instantiate a test, I am actually ending up with sort of this wrapped function that is just waiting to receive a seed and a number of runs to execute, and it'll return a list of expectations. So the first takeaway here is that because we've integrated fuzz testing into this, basically all elm-test tests under the hood are fuzz tests. It's just that sometimes when you call them, they only run once. They just run once with one value, and they don't bother generating any random stuff. But they're always set up to receive that. So that's sort of your bread and butter test thing. Then you have labeled, which is essentially a way to add descriptions. So describe is going to be working with this. So you say labeled, string for the label, the description, and then test, which is sort of recursive. So we're saying I've got a labeled with this string, and then I have a test, and then a test is one of these. So it could be another labeled thing. So you could have like when you have like describe foo and describe bar, and then finally you have your test. That's going to translate into a labeled foo inside a labeled bar inside a test, whatever. So that's basically what's happening there. So this is the internal structure that we're gonna use to represent our tests. And then finally you have batch, which just takes a list of tests and turns it into one test. So that's how you can have this entire large data structure full of tests, like with describes and all these tests put together, and still end up with, at the end of the day, just one single test. Okay, so the reason that we have this inside test.internal and not inside test, which is what end users use, is that this is using a technique with Elm modules that lets you control which things end users can do. So it lets you maintain certain guarantees about your API. So although this thing exposes all of these things, like it exposes this, it exposes this, it exposes this, so anyone who wants to can, inside of this internal Elm test project, can work with this test and this labeled and this batch and things like that, and take one of these data structures and pull it apart and do whatever they want with it. That's not publicly exposed. So if I look at my elm package.json, my exposed modules are test, test.runner, expect, and fuzz. I do not expose test.internal. So what that means is that within this project, anybody who wants to can use test.internal and everything it exposes, but once I publish the package, end users cannot use this. So basically I'm saying that I can internally write all sorts of things that use this test, that destructure it, that pull it apart, but end users can only do things with this where I've publicly exposed some sort of function that does what they want. So an example of this is filter. So filter is a pretty useful thing for taking tests and filtering it based on like a string. So I'll give it a string and I'll say I want to only come back with tests whose descriptions match this string. So that's why a filter takes a function from string to bool. So I'll just go through and run this on the different descriptions in this hierarchy, like all the labeled tests. And then if it passes, I'll keep it, and if not, I'll throw it out. So you can use this, like let's say I have, I only want to run my tests that have the word randomly in the description, or shrunken or something like that. Like I have some particular set of tests that I want to run, and I want to ignore all the others because I don't want to deal with them right now. Filter is a good way to do that, but this is not the external API that we expose. We expose a slightly different one that Actually, I guess in this case that's not true. In this case, it looks like it's just delegating out to internal.filter. Um,
For academic purposes, would you recommend anybody expose that in the package? They
uh,
went into into their node modules and or into whatever Elm uses. I'm a little weak on that.
oh, it's called Elm stuff. That's the equivalent of node modules.
Okay.
Yeah, and it's just got like your build artifacts for the compiler, like its cached stuff, and then packages, which are your downloaded packages. So that would have like Elm community shrink, Elm lang, all these various different things. Um, yeah, so basically, internal is not something that you typically want to use. It would be more common to just have this, like I would have test defined inside test, and then what I would do is I would publicly expose this test type, but not its type constructors. So the way that I would do that is I would say I'm going to expose test. So if I wanted to expose everything, I would do this. I would say test and all of its constructors. Or I would say test, and I would enumerate them. I would say test, labeled, batch, which are its three constructors. So if I did this, I would be saying, okay, not only can people have access to this type so they can use it in their type annotations, like this. So if I just say I'm exposing test, then I'm saying you can use this in your type annotations. Anybody who uses this module can do that. If I also say this, and I've got my union type defined in here, I'm saying not only can you use it for your annotations, but you can also run a case expression on it to pattern match on it and pull it apart, which means that now people can do case my test of, and then they can just like break this up, and then they can write their own case and they can take it apart and work with it. But if I do not expose these constructors, if I just say you can have the type, but that's it, then people can't sort of mess with it, except in the ways where I let them do it. So I can expose specific functions that let them do certain things to that, but not necessarily peek all the way under the hood and see what's going on. So this is a way to maintain guarantees. Basically, it's a way to say that I can rely, like as the author of elm-test, can write my code in such a way that I can safely assume that certain things are always going to be true because people who are using this literally don't have access to break those guarantees. They can't violate those invariants because I have not given them the tools to do so. So that's the normal way I would do it. The reason I'm using internal.test is that instead of just having this union type over here in test and then not exposing its constructors, the reason I'm doing that is because I actually want to use this thing. I want to destructure this in multiple different modules inside elm-test. So I want this one, this test module wants to use it, but also test.runner, runner, also wants to use it. So it's also exposing test.internal, and it's also breaking those apart in some cases. So that's sort of an important distinction. Like usually the technique is you just include the union type in your one module. You don't expose its constructors, so that instead you expose just functions that deal with it in a nice way, and then that's it. But yeah, if you need to get that destructuring ability across multiple internal modules, that's when you break it out into its own module and just do not expose that module.
Yeah, the use case I was thinking of was if somebody wanted to go to the repo for this and contribute to it to better understand like how the internals work of this, you might play around in a local branch on your own with something like that.
Got it. Yeah. So all right. So of course, all this is open source. So anybody who pulls out this code locally can do whatever they want with it. The important part is that when somebody uses it, they get it from Elm package. They're just going to basically only have access to the things that have been publicly exposed. But yeah, for local development, of course, you can do whatever you want. It's just a question of if I'm working on my application and I've added the elm-test package because I want to use these things, what do I have access to as an application developer? And that's what we're trying to manage here.
Cool.
Okay, so we've seen sort of the internal structure of a test, at least at a high level. So uh, a test has random seed, an int for the number of runs, and that becomes a list of expectations. Okay, so let's start with the runner, and then we'll see what happens from there. Okay, so we're immediately going to get into some uh, fancy stuff. So basically, so from test is this very important function for sort of kicking everything off. So basically, you've got a test, right? So the end user, what they've been doing as they've been calling test and they've been calling describe and all that stuff, all they've been returning are these tests, right? They're just building up a gigantic test, and that one test is one of these things, and that describes the structure of their entire test suite. So runner takes one of those and converts it into a runner type. And the runner is something that any of these, like the node test runner or the HTML test runner or whatever other test runner you want to have, they all use this in order to run the tests and then also produce output for the end user. And so they all need two ingredients. They need to know how many runs you want to do, and then they also need to know what initial random seed to use. So basically, the reason for this is that the entirety of elm-test is all basically using these random seeds as a way to guarantee reproducibility. So we saw earlier that there's this thing you can do where you give it a seed and it's going to it's guaranteed to reproduce these outputs. Like these exact random numbers are what's going to happen if you rerun your tests passing that seed flag. So in order for that to happen, when you get this runner instance, it's got to start with one particular seed, and that seed needs to be used to drive all of the random number generation in this entire tree. So the reason it's random.pcg.seed is so Max Goldstein is the other person who worked a bunch on this rewrite, and so he's sort of like the I think it's fair to say like the king of random numbers in Elm. He's done the most work on this, like read papers to find ways to do like 32-bit versus 64-bit like random number generation, how to get good statistical properties like good distributions of randomness from initial seeds and while still having good performance. And so he basically developed this random.pcg library, which hopefully will actually end up making it into core and just become Elm's new standard randomness library, because it's really nice. And basically, so we're saying, just give me one of these seeds and a test, a run count, and I will turn that into a runner. So I'm just going to hop over real quick and look at how node elm-test uses that runner, and then we'll hop back here and look at what it's doing with that. So in node test runner, let's see. Where is that thing? Is it an app? Yeah, there it is. Okay. So basically, inside here, when we're initializing everything, we're initializing the runner. We're getting this this test from the end user, and what we're going to end up doing with it, among other things, is calling test.runner.fromTest, passing the run count and the seed. So it's up to the runner itself to figure out the initial seed, and so the runner might, for example, take that from the CLI. So this, in this example, the end user is passing in the seed directly, and it also might just get the seed from the current time. So it might just randomly generate an initial seed and then use that. But either way, the point is the test runner is responsible for calling this function. Test.runner.fromTest that we've been looking at here. So that's this function right here. And then what we will provide for it is one of these runners. And then the runner just sort of takes it from there. So this is sort of where the generic elm-test API ends and the runner-specific logic takes over, is right here at this function call. So all the runners call this, and all the end users use basically everything else in this package. Okay, so basically this is how runner works. So you have this idea of a runnable, which is basically just a union type with one type inside of it called thunk, and thunk is just an anonymous function that takes unit, which is to say nothing useful. This is, again, in JavaScript, this is the equivalent of just saying I am a function that returns some list of expectations. So the reason that we are writing this is because, again, we're trying to intentionally delay this. We don't want to evaluate these until the runner says to. If we did not have this anonymous function wrapper around the test logic, then every time you loaded your tests, they would all immediately run one after the other synchronously, and that would be bad. So having this wrapper here, which would look like this in JavaScript or like this in Elm, means that these runnable things are just sort of waiting to be run, but they have not yet been run. So you can see kind of a similar tree structure to these runners as what we saw with the internal tests. So I'm just going to paste that in here so you can see them side by side. And actually, I'm just going to also replace runnable with this, just so you can even more clearly see it. So if you look, so we have runner has runnable, and test has test, and then they have a similar looking thing. And then they both have labeled, which is string, and then that first thing. So labeled, string, runner, and then bash, which is just a list of that thing. And so basically, the only different part here, if you take out labeled and bash, is the sort of fundamental unit. And this sort of lets you see what the difference between these two is that test has these things that are expecting to get a random seed and the number of runs, whereas runner no longer gets those. It no longer expects a seed, and it no longer expects an int for the run count. Because at this point, these are ready to just be run. So the difference between test and runner is essentially that we've gone through and we've just sort of applied the random seed and the int. So if we have one of these tests that's supposed to run 100 times, we're going to split this out into 100 runnables, each of which need no further information to go. And if we've got this random seed that's come in at the top of our program, we're going to go through and incorporate that into each of these runners, such that basically, instead of needing additional information like these tests do, so like when the end user writes the test, they're not specifying, you know, I need this exact run count, I need this exact seed for all my tests. They're just saying, hey, here's what I want my test to look like. And the purpose of converting it to a runner is to say, okay, at this point, we've decided what the seed is, we've decided what the run count is. We're just going to convert these into these things that are just ready to go. Just anytime you want, just press the button and they run. They don't need any more information in order to run. Okay. So, and that's the purpose of from test. It's to take those two missing pieces of information, the run count and the seed and the test, and then it just applies these two to all the tests in that tree, and then gives you back a runner, which is just kind of ready to go. And so that's why over here in node elm-test, once it gets these, it's like, cool, I no longer need to think about managing the run count, managing the seeds. I just need to figure out what the run count ought to be. And so because this is sort of external to the tests, I can also add a CLI flag for like -- runs, -- runs 5, right? And then I could pass that in here in the same way that -- seed, 1, 2, 3, 4, 5, once we pass that in. And at this point, I've just got these thunks, thunk being an anonymous function that doesn't take any useful arguments. It's just sort of being used to avoid evaluating things until we're ready. And then at that point, the runner has this list of things that are just ready to go, and it can just run them one after the other as it pleases. Okay, so here's how from test works. So the first thing it does is it checks your run count. And if you have fewer than 1 runs, then it just says, hey, I'm just going to give you back a test that always fails, and says, hey, test runner run count must be at least 1. You can't give me 0 runs and expect me to do something, because that doesn't make any sense, or negative runs for that matter. So that's just sort of a little validation step. Here's the more interesting part. So from here, we're basically, what we're doing is we're taking this test, and recall that the test has almost the same structure as the runner, except for this part right here, where we have random.seed and int instead of nothing. And so all we're doing here is we're just sort of recreating that structure with making the change that we want. So we're saying case test, which is to say, actually, I'm gonna split my screen here. Is that a good idea? That might be too big. Never mind. I'll just do it this way. First one is, okay, what happens if we have one of these tests? That is to say, we have one of these things. It says, okay, cool. So we're going to have this run function, and the run function looks like this. Right? It's taking a random seed and an int and returning a list of expectations. And all I'm doing is I'm calling that thing, passing seed, which is this argument, and runs. And then I'm taking the result of that and then just wrapping that in a runnable. So essentially, all it's doing here is saying, okay, we got a test, great. I know how many runs that test should have, and I know what the seed should be. So I'm just going to call that function, passing those arguments, and wrap the result in the closure. So that's how it gets from this thing right here to this thing right here. It's really simple.
It's a great separation. I'm trying to find out where the runner code is.
Oh, it's in test.runner, which means it's in, so Elm modules, like dot corresponds to slash in the file structure. So it's like test/runner.elm inside source.
Gotcha. There it is. I'll post that.
Cool. Yeah, so, okay, so that one's just sort of a one-to-one translation. The more interesting thing is what we're doing with our seed management here. Let's say that we got a labeled thing. So label's also not interesting, I guess. We're basically just saying, okay, cool. We got this sort of sub-test inside the test, and we're like, cool, we'll take that. We're gonna call from test on it, passing our run count and our seeds, and then just label the result. So that's basically, both of these are pretty straightforward. It's just saying translate from this test into a test that has the given run and the given seeds. So that means that if I call from test passing 5 runs and a seed of 1, 2, 3, 4, 5, and a test that is literally just one test where like the end user wrote like test, it works, expect true, like if I pass this as a test, then I'm going to come in here and I'm going to say, okay, we just have one single test. Let's run it, given that seed and those runs. That's it. And if it's labeled, which actually this one is, like this would be the label, then it's going to say, okay, cool. Just do the same thing with the subtest. Now, importantly, note that this is just taking the seed that we got and passing it through. And then this is also taking the seed that we got and passing it through. But as soon as you get a batch involved, in other words, like I have a describe with multiple tests in it suddenly becomes very important that I don't just pass through the exact seed that I got. Because if I do that, let's say I have, I'm going to go into example here. Over here. Sure, look at the passing tests. Oh, that's boring. Like tests, more interesting. Sure, so I have a bunch of fuzz tests in here, right? I have like this one, and I have this one, and I have this one. If I have a bunch of failing tests in here, or if I have a bunch of tests in here, I don't want to use the exact same random number generation seed for all of these, or else they're all going to get the same kind of predictable results, right? The whole point of this is to try and randomly generate stuff so we see a good, healthy range of values. And if I use the exact same fixed seed for every single one of these, that's going to be really boring. It's going to be really consistent distribution, and it's going to be harder for me to find edge cases. So what we want to do is instead of using the same seed, what we want to do is we want to distribute seeds. So this distribute seeds function. So I'm doing a fold here over, basically, I'm starting off with this tuple of an initial seed. So we're starting off with the seed that we're given. And then we have an empty list of tests. And what we're going to do is we're going to fold over this and basically say, okay, for each of the runs that we're trying to do here, we're going to distribute seeds across all of those runs and end up with a whole bunch of subtests. So let's say, just as an example, let's say that I got like a fuzz test, and it's generating strings, and it's like all strings are empty, so that test will fail, but whatever. And then I've got a test that's like, okay, cool, stir, and then I'm saying expect dot equal string dot length stir and 0. Or actually, that's okay, probably expect dot true string dot is empty. Okay, so this right here would be a really poorly written test because it's going to fail because all strings are not empty. But basically, the important part is that I want this code right here, this function, to run 100 times, and I want string to be different each time. Now, if I'm using the exact same seed to generate that string every single time, it's not going to actually generate 100 different strings. It's going to generate one random string, 100, and it's going to use that exact string all 100 runs, which is completely useless. So the purpose of this seed distribution is to say, okay, let's start with this one seed and use that seed to generate other seeds. So we're going to use a seed to randomly generate other seeds. And then we're going to distribute those randomly generated seeds to all 100 of these tests. So remember, our goal is to go from this function that actually accepts like run count and seed to use, as well as the actual test to run. And we're trying to get rid of these and just turn it into, we don't need to take any more info. And so in order to make it so that we don't have to take any more info, we need to go ahead and distribute that such that we end up with going from one of these that says, please run this 100 times, to 100 of these, each of which has their own unique, usefully different seed. So this is sort of a, we're deep in the weeds now, in case that wasn't clear. But this is sort of the most important part of making the tests both reproducible and still reliably generating random values.
So I had a question about the internal dot labeled. So like when you have a test there, can you do multiple describes? So you have like a context?
Yeah, definitely. I think I did that. Yeah, here we go. So you can say describe and then describe, and you can just keep going with that if you want. Like I could just.
So it does know to go through it again if it encounters that. Okay.
Right, yeah, so label takes a string and then a test, but a test can just be, like, one of the things that a test can be is a batch of other tests, which can include a batch of other labeled tests. So you can really just nest these as much as you want, like labeled tests, labeled batch of tests, labeled batch of labeled batch of tests. You know, I mean, you can just keep going with that as far as you want.
Yeah, I think I was overcomplicating it when I looked at the code.
It's easy because there's a lot going on under the hood. I don't blame you. Okay, cool. So yeah, so we're distributing the seeds. So we've got the run count. We've got the actual test that's going to end up receiving this new seed, and then we have a starting seed and a list of runners. Okay, so let's just start by looking at the test. So let's say that we've got we look at this test and we're like, we've just got a plain old test, no labeling, no batching, just one individual test. And it's got its run function. So remember that at this point, this run function is still one of these. It's expecting a seed and an int, and then it's got a list of expectations. So up here in the other case where we got
just one test in from test. In that case, we already took care of the run and the seed, and that was done. But remember, we're down here in batch, and in the batch branch, we have not done this yet. So we still need to do that as part of our seed distribution. So we're like, all right, cool. We've got this run function, and we're trying to do the same thing that we did up above, where we're translating it from a function that that takes 2 arguments into a function that just takes 1 and just always does the same thing with it. So seeds. Here's where we're doing that same thing that we did earlier. We're calling func, passing it this anonymous function that just calls run, passing the current seed and the run count. So importantly, this seed and run count is not the same as what we were doing earlier. This is so up here. This was the seed that we got from the end user or from the runner, whatever they said. Maybe they randomly generated it. Maybe they got it from a command line argument. We don't know. We don't care. But down here, this is the one that's coming in from this call right here. So we don't actually, we take a starting seed, but we don't take a seed. So where we actually get this seed is by calling random.pcg.step. And the step function essentially says, give me, actually, let me just bring that up. This is Max's PCG library. Gold. Max has a bunch of stuff. This Max is awesome. Okay, so we'll look at step. Okay, so step takes a random generator. So you can give it like an int generator, like if you want to generate some ints, if you want to generate some strings, whatever you want, you give it a generator for that. Then you give it an initial seed. Oops. And then what it gives you back is a tuple containing first the randomly generated value that you wanted, and then second, sort of the next seed in the sequence. So it gives you back both a new randomly generated seed as well as a new randomly generated value of whatever type you asked for. So if I say step int 0 and 100, then it says, and some initial seed, then it'll give me back, cool, here is the randomly generated int that you wanted, and also here's the next seed that you can use for your next random number generation. So we've got a brand new seed to work with in addition to some randomly generated value. So you can do this again, say step, this time passing seed 1, so the new seed that we got from the previous operation. And again, it's saying, give me another randomly generated int. I'm going to call that one y. And then another seed, which is seed 2, and that goes in here. And so we're kind of like stepping through, and we're just saying each time, give me both the value I want and a fresh seed to use for another one of these operations. So what's cool about this is that all of this stuff is completely reproducible. Like if I give this the same seed 0 value, I will get the same x, y, and z, the same randomly generated x, y, and z every single time I call this code, which is exactly what we're looking for here, because in order to have this -- seed function here, or this feature here, we need the entire code base to be based around this and completely reproducible. Another cool property about doing this, because we actually had this before we even introduced the -- seed flag, is that it means that our tests are totally parallelizable. We'll get back to why that is in a sec. Okay, so this is how we can use step to go from one initial seed in order to generate as many different random numbers as we want. Now over here, we're not generating random ints, so we're calling step. And then the generator, so in those examples, the generator we're using was int, but here the generator we're using is independent seed, which is to say, don't generate ints, just generate brand new seeds for me. I'm just looking to work with seeds here. And so as before, so in this example, it's called seed 0, but for us it's called starting seed. So basically whatever we got in from up here, that's going to be our initial seed, and we're just going to step through and generate a bunch of new seeds from scratch. So we're saying, all right, cool. So we got the starting seed, call that. So this will give us back the seed that we actually want to use. So that's the one that was generated from independent seed.
as well as the next seed to use as we continue our completely predictable distribution here. So next seed in this case would be like seed 1 or seed 2 or seed 3, this second value in the tuple. Okay, so we've now got a seed and a next seed. So we'll use the seed inside our thunk. So we've now basically said, okay, we're going through this batch of tests. First test, here's what you get. We're going to step the starting seed that we got. We're going to generate this fresh seed from that, and you get that seed. Now we've got a new seed that we're going to use to continue this process, and then we're just going to just keep going from there. So because we're calling fold L on this, that's the same thing as like reduce in JavaScript, so you could think of it that way. Basically, we're just going to run through all of these things and just keep calling this until we run out. So we're doing a fold. Here's our fold function. Here's our initial value, and then we're folding over all of these subtests. So the first test that we get, we're going to come through and say, okay, you have 100 runs, and you're this particular test. Cool. Here's our starting seed, and we're going to generate the actual seed that you get. So you do not actually get the starting seed. You get this next thing to flatten you out from a function that takes the run count and the seed into just a plain old thunk. And that's going to be what we add to our list of runners. So we've got this sort of ongoing list of runners as part of our fold, and it starts off empty, but as we fold over subtests, this list gets bigger and bigger and bigger. It gets more and more runners. And so when we do this, we're saying, okay, each test gets translated into a runner with its own individual seed. And then finally, the last part of this that makes this all work is that when we return from distribute seeds, what we return is not just the list of runners that we produced, but it's also the next seed to use. That's sort of the critical element to actually ending up with different seeds, is that not only do we say, okay, cool, we started off with this list of runners that was empty and we want to add one to it. If we want to add a new runner, so now we have translated this test into adding it to our list of runners. So that's part of what we need to do. But the other really important part is that we need to remember the next seed that step gave us and return that. And that then becomes the starting seed for the next iteration of the fold. So let's say we've got test 1, test 2, test 3. When we call, and we've got these in like a describe batch. So just to walk through this, so test 1. So this is what subtests would be. It would be test 1, test 2, test 3. So let's just put a little comment there. Okay, so we've got these 3 tests because we put them in a describe, and that's describe resolves to a batch under the hood. So we've got actually describe resolves to a labeled batch if you're wondering how that works. So that's like describe just says make a batch of tests and then put a label on it. So we get to the point where we're like, all right, cool, we got these 3 tests and we need to distribute seeds to them such that this test is running with 1 seed and this test is running with another seed and this test is running with a 3rd seed. Basically the way that we're going to do that is first we take this test and we're calling distribute seeds on this whole list of subtests. I'm going to pull this out of the pipeline just so you can kind of see the call to fold in isolation. So this is what's happening. So we're like, all right, cool. So take the subtests, fold over them. So first up is test 1. So test 1 comes in here. The run count is always the same. That's coming in from the argument to from test. So that never changes. So if you request 100 runs, that's always going to be what comes in here. Okay, so then we get test 1 comes in here, and test 1 is now inside of our test. Our starting seed is going to be this, because this is what we use to kick off the fold. So that's, again, the seed that was passed in. So that's our starting seed. So let's say seed is 1, 2, 3, 4, 5. And then, of course, the empty list is what we're starting off with our list of runners because we don't have any runners yet. We're about to start building them up. So test 1 comes through here, and we look at it, and we're like, okay, what kind of a thing are you? You are an internal.test. You're just one individual test. Cool. And you have this function called run. Great. Run is expecting, again, a random seed and an int, and int for being the run count. So we're going to give you a new seed and pass through that int as the run count sort of uncritically. So all right, cool. Hello, test one. I'm going to generate a new seed for you. So call step, passing independent seed because we want to generate a seed. And then we're using this current seed that we got to work with as our starting seed. So step says, okay, cool, got it. You want me to make a new seed based on this starting seed. So it says, here you go, here is your new seed. Also, if you want to step some more, which we certainly do, here is the next seed to use for the next time you call step. So like, cool, got a seed now, excellent. We will translate that into the runner version of tests, which is all this, and add that to our list of runners. And now we've got one more runner, which no longer needs any further information in order to run. It's already got its run count and the initial seed incorporated into it. And finally, we return next seed that step gave us back, so we can use a different seed next time. So like, cool, all right, great, that one's done. So test one, cross it off the list, we're good. So test one is done. Now we have test two and test three left. But now we have runner one, right? That's in this list over here. Also, this seed value, because we returned next seed, which step gave us back, this is now a different seed. So maybe this is like 99576 or something like that. So now we go to the next iteration of the run. We're like, all right, cool, test two, you're up. But now test two is getting a different starting seed. It's getting the result of next seed from test one. And so it's going to go through this whole process again, except this time when it calls step, because it's getting a different starting seed, it's going to return a completely different seed for test two. So when test two gets its thunk, it's going to have a different seed here because the starting seed was different. And then it in turn is going to make yet another next seed. So now we've got runner two. So test two has now been converted into runner two, and we've got yet another seed. So 846, that's not a 6, that's a different number. I know how numbers work, I promise. I shouldn't promise that. And now we've got yet another runner count. And yet another runner. And then finally, we get through test three, doing the same process. And now we've got yet another seed of one. That's, again, okay, numbers are hard. Runner three. And so now we have folded our way all the way into having no more seed lists remain. Sorry, no more tests remaining in our list. We've got yet another brand new seed, and then we've got finally the list of runners that we were going for all along. And each of these runners now has their own thunk and their own thunk with their own seed. So they'll actually produce usefully different values when we run them.
Now the tests aren't going to know like anything about the other tests, though, right? If you're doing a unit test. Right. Yeah. They don't implicitly have any dependencies. If you want, of course, you can write. I could write a test that's like some constant equals 5, and I could have multiple tests reference that just because it's in an outer scope. But as far as like the test authors are concerned, they have no idea that any of this seed distribution stuff is happening under the hood. This is all completely transparent to users of the library. Yeah, I was getting confused as far as because it's a lot of meta programming, so it's a lot to follow. I can see how it would be confusing. Yeah, I mean, one of the design goals was to try and insulate the users of the library from this, because it's like basically our feeling was just sort of that it should sort of just work. Like it should feel pretty straightforward to use. Like you're just like, I want to think about my describes and about my tests. I don't really want to worry about random number generation and all that stuff. I want it to just work and do the right thing. So when we were coming up with this API, that was sort of one of the goals, was to make sure that, to be very careful to design the API in such a way that we could do a whole bunch of really complicated stuff behind the scenes, so that people who are using the library can get this experience of you just write tests in a way that feels pretty straightforward, and all of these features just sort of work really well for free. And so this is the this is the work that goes into making it nice to use for free. Yeah, I love it's like really complex, but looking at the code, I feel like I understand what it's doing. Like the way you're describing it, though, I'm going through the code. I'm like getting, if you weren't there, I'd probably be like, well, I don't know what everything that's happening, but each function individually, I could see, okay, this is supposed to do this, and the documentation is there. It's like when I like RSpec for Ruby with describes and context and everything in there. That's a lot to swallow when you look at the source code for that.
Oh, I bet. Yeah, I've used RSpec, but I've never actually looked at the code. Yeah, it's interesting to know. I've never like worked on a test runner for, or I guess like never like built one from scratch for any other language. So yeah, interesting experience to say the least.
Yeah.
Okay, cool. So anyway, so at this point we're sort of done with the seed distribution. We end up with this extra final seed as the last iteration of the fold that we don't need. So second is just like, hey, take a tuple, give me the second thing, which is to say the list of runners, because at this point we don't care about that final seed. We're not iterating anymore, so we're done with it. So we just say second to sort of throw out that first value and just keep the runners. And so now we've ended up with runner 1, runner 2, runner 3 from where we started out with, which was test 1, test 2, and test 3. And now we can just batch those runners together, and we're good. Oops. Elm format is awesome. I don't know if you've used Elm format, but it's basically for automatically formatting your code, and it's cool in a number of ways, not least of which is, so let's see, let me do something drastic. Yeah, so I've got distribute seeds run. So let's say I just like put this down here and then I put this over here and I'm like indent this in a crazy way. When I save, it just sort of fixes everything and just formats it in a consistent way. So like I can put that there, or do this, or maybe I have like a bunch more spaces than I need and I just hit save and it's just like, okay, I will clean things up for you.
It's an extension for Atom? Is that what you're
I have an Atom plugin that actually it's pretty standard for Elm text editor plugins to run Elm format on save if you have Elm format installed. So if you just let's see.
Now when I look at
go
ahead, sorry.
Yeah, that's it. So you can just it's got a list of all the different plugins and how to use them with Elm format and stuff. But yeah, usually it just sort of works by default. Like if you just install it, as soon as you hit save, it'll just do that for you. And yeah, it's great. What were you saying?
No, I was just saying, like, I use for JavaScript, I use Jasmine, or I'll use Mocha with Chai or something. But it's and sign on sometimes. If I'm not using Jasmine for mocks and stubs, and there's so much you can do with testing, and there's so many different opinions. I like that, like when I look at your docs, it's very easy to follow. There's not a lot of things, so I feel like you could have a whole bunch of extensions built on this to add a lot of other types of testing.
Yeah, I mean, yeah, actually, so the author of Elm format, he's also written a library for testing effects. Yeah. So yeah, there are definitely different types of things that you can write. Yeah, it's sort of a interesting field to work in because there are so many like opportunities to do things differently. Because basically, as far as the Elm community goes, it's sort of like it's. On the one hand, it's got a lot of familiar things from other languages, but on the other hand, there are a lot of things that make it pretty unique. And so there's this strong culture of let's have nice tools that we make from scratch. And until we can come up with like a really nice thing, we'll just use like a workaround rather than sort of meeting halfway and trying to come up with something that's sort of okay and like maybe something that we might later regret having committed to. And so that's kind of the culture of how to develop things and sort of grow an ecosystem that gets nicer and nicer over time. And so that's sort of what's happened with elm-test, where the original elm-test was just sort of
like very minimal, and it was just like, here is you can run some tests, and that's it, and they'll give you output of like whether they passed or failed. And then when we set out to redesign it, we were kind of like, okay, let's really take our time and think through the API and try to make really good decisions about these things. And so the development process was actually we made this thing called Project Fuzzball, which was the basically it was a library that was going to become the new elm-test, which is why it's now deprecated. But we basically used this as a way to iterate separately. We actually got all the way to version 7.0 with this before we were we were done and ready to merge it back in as elm-test 2.0. And so just by doing this as this sort of separate thing, we were able to try it out and like have people use it on real projects and get a feel for whether the API was nice, whether it was working, and stuff like that. So once we did merge it in, we had a lot more confidence that we'd actually built a nice thing that was ready for lots of people to use. And so far, it's seen a lot of enthusiastic responses. So they're pretty sweet to see.
Yeah. I mean, would you recommend testing like a lot of times on doing front end projects, like if you're doing a web, a web application, you'll end up testing like end to end functionality, like with HTML. Sometimes in React, if you're using like Enzyme or something, you'll test the actual rendered output, which some people like and others don't. Is there something like, do you recommend testing that way with Elm, or is it not something you should really do in the Elm philosophy?
Oh, totally. Yeah. I mean, I definitely recommend actually testing on like a real DOM, as much as possible. I will say that people have pointed out to me that there is an important consideration for how long your tests take to run. And you can get a ton of mileage out of just testing like views in isolation as far as what they cover, and the difference in terms of test execution time is really substantial. So I view it as basically, in an ideal world, test on a real DOM, because that's going to catch things that sort of just testing the view by itself can't catch, like browser specific problems or timing problems, things like that. That only come up when you have a real DOM that you're working with. But I also recognize that that can make your test suites take a long time if that's the only way that you're testing those things. So testing like views in isolation makes sense to me at a conceptual level as a time savings measure, as a way to basically make sure that you're getting good coverage, but still having reasonable test suite execution times. But so elm-test, this library that we're going through, is not concerned with views or testing effects or anything like that. It's really just sort of like business logic tests.
Yeah, that's why I was asking, because I know like this looks great for like unit type tests, and then I'm like, well, if you were going to be in an application and you wanted to have these other types of tests, you'd probably make something built on top of this, or you'd make a separate module to do that sort of stuff.
So I have not used it yet, but I've been talking to him about it. WebDriver.
Yeah, WebDriver.
So
cool.
Yeah, Lorenzo's been doing a similar thing to elm-test, but basically for doing WebDriver type tests for actually running stuff in the browser. I don't honestly know where he is with this right now, but it seems like an interesting project to follow for sure, if that's something you're interested in.
Yeah.
So at work we use Capybara because our backend is in Rails. I work at No Red Ink, by the way. We're hiring. Shameless plug. But basically, so even though our front end is now mostly in Elm, actually we're at like 36,000 lines of Elm code production. We're still almost exclusively Rails on the back end. And so Capybara is sort of the go-to for end-to-end tests for us, because that lets us actually call the Rails code to set up the database in the right way and so forth.
Yeah, I've used Capybara. I really liked it. There was a lot of, I was using it with Mechanize before these other tools came out, and it was really easy to use. It had nice API.
I've actually not used Mechanize, just Capybara.
Well, it's just a headless browser.
Oh, got it. Cool.
So,
Okay.
I mean, is there anything else in the code that we need to go through before we end this?
I think one more cool thing to look at is so we've now sort of done the C distribution. I just want to quickly go over in the node test runner something that I think is pretty interesting. So one of the things that we talk about a lot in the Elm community is how to leverage the JavaScript ecosystem. And so you might notice that when we're running the CLI, we have colored output here. And what I'm using for that is chalk.js. So if you've not used Chalk, it's sweet. It's basically a library for colored output in the console, but it has a lot of really cool, useful features such as detecting when it's on a CI server and not trying to print these out. Because if you've ever seen like Travis or Jenkins output that's just full of all of these like random garbled characters, that's when it's somebody who has not done as good a job as the authors of Chalk did. Detecting that and not actually spitting out those characters when they're just going to show up as garbage. And so that means that I can have this code and it does a nice thing in the console where it's nice colored output, but when I run Travis tests with these, it's just also looks nice, except it just has no colors. And I appreciate that because like having had to run like certain JS test runners with like -- no colors or something like that to try and fix that, I like that it just works. It just does the right thing. And so I wanted to use Chalk for this, which means that I needed to interoperate with it. So Elm is not designed to run on Node. It's designed to run in the browser, but since it just compiles the JavaScript, if you want, you can run it on Node. And it has this system of interop called ports, which is basically where you talk to your JavaScript code using sort of a client-server metaphor where you just send data back and forth. You say like, hey, JavaScript, here's some data. And then JavaScript says, cool, hey, Elm, here's some data back. And that's how they communicate rather than like direct function calls. So what I did is I set up, I wanted to use Chalk for this. So if I look at my package.json, I'm using Chalk as a dependency in my test runner. And the way that I'm talking to Chalk is basically I set up this thing called chalk.elm. And basically what I'm doing is I'm just, I'm passing in, I'm like, hey, I want to have these styles. So Chalk has like a list of styles. So like bold, italic, underline, various colors, and then the actual text that I want Chalk to spit out. So basically I made this little thing that, given this sort of Chalk record where I'm just like styles is this, text is this, it will encode that and send it over into JS land. So it'll send it from Elm to JS. And where is my Chalk? Yeah, right. So then I wrote this function called Chalkify, and it takes a list of these from Elm. This is just raw data from Elm. And then it maps over them and says, okay, look at message.styles. So that corresponds to this list of strings. And then, oh, right. We also have to do special handling for Windows because Windows shells don't have like support for things like this nice, this is 3 different like box drawing Unicode characters. But in Windows, we have to translate that into a pipe, and it can't look contiguous. It looks like that in Windows, which is not as nice. At least it doesn't break and look crazy like it would otherwise. Anyways, that's the Windows handling. But yeah, so then basically what we do is we say like path.forEach, and then we just basically look up the next thing in Chalk, the next object field in Chalk based on these styles. So basically what that means is that if I give a styles of like green, bold, that's going to end up translating to chalk dot green dot bold. So that's what I made this little interop layer that basically does this. And then eventually I run out of path things that I specified, and then I call it passing the text. So essentially what this lets me do is if I just look at the chalk API, so you have like chalk.blue, chalk.red, chalk.underline.bgblue. So anything that I see in there, I can now represent in Elm by saying styles equals, and then you just translate this instead of dots into a list. And then text is, hello. And what this will do right here is using my little interop layer, it will translate into world, right? So to keep that consistent. Oops. Yeah, so basically doing that will translate, will result in this being called. And so I ended up, just by doing this, I make it so that my Elm code can now really easily leverage chalk and use that to get all my nice colored output and all the benefits of chalk and everything else. And I wanted to point this out because I haven't actually seen people really doing this much on Node. Like some people are doing Elm CLI stuff, but I don't see a lot of people like trying to actually make use of first-class like JavaScript libraries on a Node platform using ports like this. But I just wanted to demo that actually, yeah, it totally does work. And it's a totally reasonable thing to do if you want to make nicer CLIs for your Elm code and still, write as much Elm code as possible, which certainly like the Node test runner is, obviously lots of Elm code because that's how it makes more sense to me to write it. Yeah, so that's kind of the highest level like walkthrough of elm-test. Obviously, there's a lot more going on there, but hopefully that was useful.
Yeah, I thought it was really cool actually. I've seen chalk used in Yeoman, but I haven't seen it in a lot of projects lately. But it is very, very cool, and it looks like you didn't have to do. I mean, I'm sure it took a lot to figure it out, but it looks like you didn't have to do a lot of code to get it to work with Elm, which is really surprising.
Oh
like,
yeah,
I would think that it would be huge to go back and forth, but that's pretty cool.
Yeah, no, it was honestly, it was like kind of the first thing that occurred to me was I was like, all right, so Chalk has this API where it's just, it looks like this. I'm like, that seems pretty predictable. I can just represent this as, a list of strings and then just call it in JS. So I'm like, all right, I'll just do that. And as it turned out, it was pretty nice to work with. Like even, something like this, chalk.blue.underline.bold. It's like, okay, that's just 3 strings. So works for me.
Awesome. So if people want to get in touch with you, if they want to find you, stalk you, whatever, where can they get you?
Twitter, RT Feldman. Same on GitHub.
Okay.
And yeah, that's me.
Excellent. And so you have like a Webpack Elm thing on your personal one, which is pretty cool.
Yeah, we're also using that at work. Webpack loader. It's yeah, the Elm ecosystem is really coming along. I'm pretty happy to say that it's not only getting bigger, but also maintaining quality. Like I'm still very happy with like the average experience of using some tool that the Elm community's put together. So I'm glad to be a part of that tradition, and hopefully I'm doing a good job keeping it up.
All right. Well, thanks for coming on. This has been episode number 22, elm-test, and I posted all the links in case you want to go back to those files that we were looking through. That's all on the Google Plus page for this event. So thanks, everybody.
Awesome. Thanks.